Okay, let's go to page 248, and this is section 21.3. This deals with input and outputs. Okay. Your input is called the domain, and your output is called the range. And sometimes the domain has a restriction, okay, and that would be not allowed. For example, if you have f of x equal to 1 over 1 minus x squared, so in this case your domain, so in this case what you can do, you can factor, so you got 1 plus x, 1 minus x, okay? So you can see that when x equal to -1, this is going to give you 0, or x equal to 1 will give you 0. So this is not allowed. So domain would be all real number except plus or minus 1. Okay. So domain would be all real number except for -1 and 1, because this would give you 0 in a denominator which is undefined. Now let's go over some examples. So example 21-3. So it says, what is the domain of log of x? Okay, so to find the domain, again, you can set it equal to y, and you can switch the base. Okay, so when you don't see the number, means it's base 10. So that's an invisible 10. So the base always stay. Okay, base do not move. And so you just crisscross, so you're going to get 10 to the y equal to x. Okay, so from here you can see that the x would be greater than 0. Okay, x has to be greater than 0, because no matter what y is, you can put whatever the number y. So let's say if you put y equal to 0, you got 10 to the 0 equal to 1, right? Now, if you were to graph that, so again, if you let y equal to 0, then x equal to 1. Okay. If y equal to 1, so you're going to get 10. So y equal to 1, you're going to get 10 over here. Now, if y equal to like -1, so y equal to -1, you're going to get 10 to the -1, which is equal to 1 over 10. So it's 1/10. Okay. So it's going to be like over here. So your graph is going to look something like this. And it will never equal to 0. So that's a big drop off right over here. Okay. So you can see that x will always greater than 0. Okay. So x equal to 0 is your asymptote. Okay. So you will never touch that. So again, so that's your domain. Okay. So sometimes there are many ways to get a domain. Sometimes you can just go and factor and look. Sometimes you have to kind of sketch out and think about it. Sometimes you have to switch the base. Okay. Okay, let's go to the next example. Okay, let's go to example 21-4. You want looking for the range of 2 to the x. Okay. So you can kind of think about it. So you got y equal to 2 to the x. Now, you can make a table and sketch out, for example. Okay, so if x equal to 0, you got 2 to the 0, you get 1, right? So x equal to 0, you get 1. Now, and if x equal to 1, y equal to 2, right? If x equal to 3, you get 8. Wait, 1. Let's do 2. You get 4. Now, what happens if x equal to -1? Okay, so -1, so you get y equal to 2 to the -1, so y will equal to 1/2. So at -1, you get 1/2. So notice you're never going to get negative, right? And then if x equal to -2, then you got y equal to 2 to the -2. So y equal to 1 over 2 squared. So y equal to 1 over 4. and so forth and so forth. So you can see the pattern. So negative 3 will give you 1/8. Okay, so this is going to be like this. So the range is a y value. So here's your y, here's your x. So you can see that the range is y greater than 0. Okay, just the it's a it's similar. It's like the inverse of this one here. But notice that flip it over. Okay, in a way. Okay, similar. Okay, this is a log function. If it's an exponent function, if it's a log base 2, then would be the reflection of it. Okay, or the inverse of it. Okay, so anyway, so the range would be y greater than 0. Okay, now let's go to the warning right over here. Okay, on page 250, just be careful about the notation. Okay, so before that, let's go and do this example. Let's do example 21-5. Example 21-5, it says, if f of x equal to x plus 2, then f6 of x, so this will equal to x plus 2, so that's the first layer. Then you have the plus 2, that's your second layer. Okay, plus 2, that's your third layer. Plus 2, that's the fourth one. Plus 2, that's the fifth one. Plus 2, that's the sixth one. Okay, so it means you have to keep repeating the same function 6 times. And so f6 of the x equal to equal to x plus 12. Okay, so just kind of be careful with this notation over here. Okay, now the warning that I was talking about earlier. Okay, so it says fn of x is not the same as f of x n. Okay. Okay, so fn of x is not equal to fx to the n power. An example of that is in example 21-6. So let's say if f of x equal to x squared, then f3 of x will equal to x squared square, so 3 times. So this will equal to x to the 2 times 2 is 4 times 2 is 8. Okay. Whereas f of x to the 3 power this would be x squared to the 3 power. So f of x to the 3 power equal to x to the 6. Okay, so they are not the same. So you have to be very careful. But this notation does not always use it this way. Okay, so in the warning, it gives you the kind of the sign function. Okay, so according to this, right? Then sine square of x. Okay, again, so the sign of the trigonometry function used differently. Okay, technically, if you follow that, this would be equal to sine of x. Okay, but that's not what it means though, because this is very rare. You almost never see this before in trigonometry. You probably never come across this. This is extremely rare, and because of that, so sine square of x is equal to, it means sine of x times sine of x. Okay, so in the trigonometry function, this is used as this way, not this way. Whereas in algebraic, it's used, in algebraic, this with a number is used this way. Okay, in the trigonometry, it is used this way. Okay. Okay, but normally, again, if you see these, would be these, not these, except in trigonometry. In trigonometry, would be like this way. Okay, so it's kind of a little bit confusing, but just be aware of that. Okay, and again, the reason because mathematicians usually kind of lazy. They want to do a shortcut, and so since this shows up so often, they just use this notation for these instead of this, because this probably never show up. Okay, you probably never come across these. So just be aware of that. Okay, let's do. Let's go and do one more example. Okay, example 21-7. It says suppose f of x equal to 6x squared and g of x equal to x over square root of x plus 1. Okay, then this is called a composite function. Okay, so you're looking for so the way to say it, this is g of f of x. Okay, so the way to do that is so this is the way to write this is g of f of x. Okay, so just line up straight, and that's it. So that means whenever you see x, see over here, this will match, right? So now this will be f of x. So this becomes g of f of x. So this becomes f of x over square root of f of x plus 1. So again, whatever is over here, they have to match. See that? It's matching, right? And then after that, you can go and change, right? So g of f of x, then you can come up here, so it would be 6x squared over square root of 6x squared plus 1. So g of f of x is equal to, and you can simplify this, x can come out, so it would be x square root of 6 plus 1, and the x can cancel out. Oh wait, no, cannot cancel, this is term. If there's no plus 1, it can cancel. But because of plus 1, these are terms, so you cannot cancel anything. And so that's it. Okay. And as I mentioned before, okay, now just this is a side note. So g of f of x, most of the time is not equal to f of g of x. Okay. So again, usually, okay, in some rare cases by coincidence they are equal, but most of the time they are not equal. Okay. And again, best illustration is when you're doing your laundry. Okay, if you put in the washing machine first and then put in the dryer, you're going to come out nice, clean, dry clothes. If you put in the dryer first and then you're going to put in the washing machine next, you're going to come out clean, wet clothes. So you can see the results are not the same when you reverse the order of the function. Okay, so just be aware of that.